different parts to this. Actually, as a lead-in, let's do the classic warm-up. This just, it's not in your homework, just mentally saying this here. So this is the graph of f. It is an integral, g is an integral defined function. G is sometimes called an area accumulation function. All right, what if I said, what if the question asked, where is G increasing? How would you go about that? And how would you show the appropriate calculus to back it up? Okay, so let's start with the big idea of calculus. Big idea of calculus is G is increasing where? Nope, you're too far ahead of yourself. G is increasing where G prime is positive. That's the big idea of calculus. Something is increasing where its derivative is positive. Then connect it to what's given. What is the G connection to F, or G prime connection to F? G prime, which equals F, is positive, and that's on negative 3 to 1.5. It would not read for the endpoint, so if you use parentheses or brackets, you'll be fine. What if they asked you, where is G concave up? Big idea of calculus is G is concave up where? G double prime is positive. What is G double's relationship to F? F prime, or the slope of F, if you like to go all the way back to F, is positive on what? 0 to 3. Negative 3 to 0. I don't know why I listen to you people. Negative 3 to 0, yes. Okay, cool. What if I asked, where does G have an inflection point? Inflection point at, or where? G double changes sign, or G double, which is equal to F prime, which is equal to F slope, changes sign, and that's at x equals 0. Okay, cool. Alrighty. What if I told you that F is periodic with a period of 6? And I asked you, what is G at 21? Ready? Your answer?
4.
Say approximately 4. Okay. Others? Think about it.
Wait, figure that out.
I'd start by putting 21 into what G is defined as. So G is an area accumulation function. How much area is accumulated every period of G, every period of F? 9 pi over 4. Okay, do you agree that every period, these areas knock each other out, and so you, in essence, get a quarter of a circle every period, 9 pi over 4 per period, right? How many periods? Now you're starting to make me mad. Negative 3 to 21 is how far?
24.
How many periods is if a period is 6? 4. So it's 9 pi over 4 area accumulation every period times 4 periods. 9 pi. Okay. Let's go on to fundamental theorem of calculus part 2. Do you know the fundamental theorem of calculus? All right. It is sometimes subscripted or subtitled, not subscripted, subtitled the existence of the definite integral. It was where the existence of the definite integral was defined. For example, if I said, hey, what is this definite integral equal to? It is minus 0, because when you do a definite integral, you take the antiderivative and evaluate it at the upper minus lower, yeah? That's the fundamental theorem of calculus. It has, on the most basic level, what you do. The meanings of it are a million layers deep, but on the surface level, that's the fundamental theorem of calculus. To evaluate a definite integral, we take the antiderivative at the upper minus the antiderivative at the lower. The fundamental theorem of calculus part 2 you've been using, in fact you just used, and that is the idea that the derivative and the antiderivative are inverse operations. They undo each other. Let's go to a couple fundamental theorem of calculus part 2 exercises. If I said what is the derivative of this integral defined function, let's do it once the quote-unquote long way. Working inside out, what is the antiderivative of t squared minus 3t plus 1? Okay, from 0 to x, and then do I take the derivative or do I evaluate it at x and 0? X and 0, when I evaluate it at x, I get 1/3 x cubed minus 3 halves x squared plus x, minus, in this case, a bunch of zeros when I put 0 in. And then when I take the derivative of that, I get x squared minus 3x plus 1. So it seems like they undid each other, and it's just like the original, but with x in instead of t. Right? All right. The shortcut then is just to say, well, it's just like putting an x in, because the derivative and the antiderivative undo each other. So with that said, the shortcut here is sine of x cubed. Tell me, why could I only do the shortcut here? Yeah, what is the antiderivative of sine of t cubed? There isn't, it's not integrable. Not everything has an antiderivative. And I don't mean you can't do it. I mean Newton himself couldn't do it. It doesn't have, there isn't an antiderivative, period. Okay? The best you could do, if you get stuck and wanted to think your way through this, the best you would do is you would say something like, let f equal the antiderivative of that, which I have no idea what it is, but it's okay because I'm going to take the derivative in a minute. And if you get something that's non-integrable and you want to go through it the long way, then that's how you would approach it. You would just kind of define. You might say, why would I ever want to do it the long way? You'll see. Let's go here. The log of the arctangent of t from 5 to x, what do we get? Arctangent of x. So you're saying that doesn't matter 0 or 5? Doesn't matter? Doesn't matter. Why doesn't it matter? In terms of the long way. Yeah, even if it was 5 and I had some kind of thing, expression with a 5 in it, what is then the derivative of that thing with 5? It's derivative of a constant, so it's still 0. Doesn't matter, it's still a derivative of a constant. All right. If I have a little switchy switch, then if I were to do this the quote-unquote long way, yes, I know I could switch the limits, but let's talk about why you switch the limits other than what you were told to do. So what is the antiderivative of t squared minus 3t plus 1? Same thing we just said. I hear you. All right, way to save yourself. All right, from x to 4, yeah? So I would get something like 64 thirds minus 48 halves, or 24, plus 4 minus 1/3 x cubed minus 3 halves x squared plus x. And then finally I take the derivative on that. And when I take the derivative, I get negative out front of 1/3 x cubed minus 3 halves x squared. No, I didn't take the derivative, dummy. Sorry. Just started rewriting. The opposite of x squared minus 3x plus 1. So shortcut-wise, we could say that when the derivative, when x is in the lower limit of integration, then it's the opposite of the same function with x in, yeah? All right. With that said, what is this derivative? Negative cosine of x cubed. And how about this one? Negative log of squared minus 3. As a multiple choice, what other possibility might it look like? Over x squared minus 3. Okay. All right. Let's at least function within a function. I would like you to actually understand why you do what you do in the shortcut. So again, we'll do it the long way. So this first one, what's the antiderivative of cosine? Sine or negative? Sine of t from 2 to x squared. Next, I have put in x squared and 2, so I get sine of x squared minus sine of 2. And finally, I take the derivative. Now, when I take the derivative, because I just put a function within a function, I'll have to use the chain rule. So what is the derivative of sine of x squared? 2x cosine of x squared minus 0. All right, so we can see that we have, when there's a function in the limit position, we must use the chain rule on that. So, go ahead and do those other 4. I don't think we need to do another one together. You can do those 4. Exchanging glances, wandering in the night, like a chance, maybe shadow, before the night is through. Something else, it's so nice, something sweet, so exciting, something in my heart. These are Okay, how we doing? Which one are we on? 2, 3, 4, or 5? Or none? Okay. Kevin, what'd you get for this one? What? Oh, sorry. Yes.
Cosine x log sine squared x
I'll go with science for times 3. Cool. Okay. Trying to think about this one. 1 over 2x cubed
Oh, yeah.
times derivative of the inside. 6x squared. Bandy, bandy. Okay. Eileen, I've never heard you speak before in class. So here we go. Go. 2? What's it say? I can't see. E to the x. Okay, sorry, go ahead. 2? Why is there a 2? Let's go here. So arctangent of e to the x squared, yeah? But then times derivative of the e to the x only. So just times e to the x. So, oh, just so we're clear, sorry, I forgot to mention this. When I say chain rule, make sure you don't take the derivative of this whole thing inside with the square. It's just of what's there only. So only of the upper limit. So e to the x, yeah? Last one. Sine of square root x minus 2x plus 1 sine of x squared plus x. Cool. All right, that's pretty gross. Let's do one more that's been on the 8. Oh, shoot, I forgot to paste it in. I think you have it on your paper, but I don't have it. It's at the top of your second page. It's a limit as x goes to 3. The top is an integral from.
3 to 2x minus 2x, but
Would you change that 3 to 0, please? And of some kind of function, what was it? F
e to the x to the c squared.
e to the x squared. T squared?
Yeah,
T squared.
dt
3t over.
3x minus 9.
Okay, wonderful. All right. So, it's a little wacky. It's kind of kooky, but I don't know. Just do something. What can I do? What's the first thing you would try? Just evaluate. Try and direct substitute. If you direct substitute, what does the top look like? 0. Why is it 0? Upper and lower bounds are the same, so the rectangle has basically 0 base. So it's got to be an area of 0, and the denominator is 0. And 0 over 0 is 0, right? No, that's definitely not supposed to be. That's not supposed to be. No, silly Mr. Rickman, that is indeterminate, and we must use L'Hopital. So the limit as x goes to 3 of 0 to 2x minus 6 e to the t all squared dt is 0. The limit as x goes to 3 of 3x minus 9 is 0, and therefore I have justified in using L'Hopital. By L'Hopital, the problem is equivalent to, what is the derivative of the top using fundamental theorem of calculus part 2? Squared times 2, because we've got a chain rule derivative, right? The derivative of 2x minus 6 is a 2, and the bottom is 3. Now it's evaluated at 3. I get e to the 0 squared times 2 over 3, which is 2/3. Okay, cool. All right, switch gears, totally unrelated topic. I asked you, what is natural law? What is it? It's the inverse of exponential. It's the inversity. That is the classic definition. And for several hundred years, 400 years, that is how they would have defined it. It's the inverse of e. once calculus was defined and created, and they started within a generation, just people were doing calculus all over the place and using it in totally different ways. One of which was applying it to natural log. Now, it was known that the antiderivative of natural log is 1 over, or the derivative of natural log is 1 over x. After a while, people found it better and easier to define log totally differently. Instead of the inverse of exponential, log started to take on, at least at the higher levels, the definition of 1 over t from 1 to x. Now, why would you do that? Well, I'll get to that in a second, but first, can't you agree that that is true because the natural log is the antiderivative? And if I evaluate that from 1 to x, it's natural log of x minus natural log of 1, which is natural log of x. Now, more importantly, though, conceptually, is every natural log then takes on a different meaning. When I say natural log of 2, now, instead of thinking of it as, all right, e to what power would be 2? Well, 2.7 have to be a little less than. Instead of all this e to what power is this number, like you normally would think, instead you now think of natural log of 2 as the area under this curve from 1 to 2. And that blue area, that's equivalent to the natural log of 2. And if I wanted the natural log of 7, well, that's equivalent to if I graphed this graph and went from 1 to 7. That shaded area is equivalent to the natural log of 7. Now, that's useful because if you use it in conjunction with trapezoids or some kind of other estimation method, you now have a way of calculating things that normally were done by these crazy long tables. Natural log of 7, in the old days you would look up a table of logarithms and say natural log of 7 is approximately this. And they had a much more accurate way of calculating these without the table. So it goes like this. If I wanted you to estimate the natural log of 4 using 3 trapezoids, then you could say, well, by this new definition, natural log of 4 is the area under the 1 over t curve from 1 to 4. Now that, used in conjunction with the, why don't I just integrate this? Why do trapezoids at all? Why don't I just integrate? Because then you get natural log of 4. And while that's true, it's not very helpful. Natural log of 4 is itself. That's great. We want to estimate this. Now, using more numerical methods. So if I go from 1 to 4 using 3 trapezoids, what's delta x? 1. I also divide out the 2 by virtue of the trapezoid formula. We always do that. I didn't say, but we're going to use 3 equal subdivisions. If I let f equal 1 over t, then my inside, or my parallel bases, are f at 1 and 2f it, 2's, 2f it, 3's, and a single f at 4. All right, so 1/2. F is 1 over whatever you put in. So f at 1 is 1. 2 times f at 2 is 2 times 1/2 will be 1. I see what you're saying. That's not what I asked, but okay. F 2 times f at 3 is 2 times 1/3, and f at 4 is just 1 over 4. All right. What's the common denominator? 12. So the 1 we would multiply top and bottom by 12. It stays 12. It becomes 12. The next one, same deal, 12. 2/3 I multiply top and bottom by 4, becoming 8. And 1/4 I multiply top and bottom by 3, becoming 3. All right, so all together, what's the numerator sum? 35, I agree, over 12. When I then multiply, my estimate is 35 over 24. Let's see just how close we are. 35 divided by 24 is about 1.458. Log of, natural log of, what do we do, 4? 4 is 1.386. So we're, what, about 700ths off? That's pretty good. 700ths. All right. Now, it also allows us to figure out how close were we. If we want to find an upper bound for the error in our estimate, then we use our trapezoid error bound idea. Do you have that in your head yet? The error is less than or equal to
B minus A.
B minus A cubed over
12
times M. All right. What is B minus A in this case? 3. And what is N in this case? 3. And M, we're going to have to do some side work. So what is the function? Okay, this is a very common source of error. So what's the function? Is it natural log or is it 1 over t? 1 over t. Okay, the function is not what you're integrating. We're integrating 1 over t. F prime is negative 1 over t squared, so F double is 2 over t cubed, right? Unless I made a mistake. 2 over t cubed. What is the max on 1 to 4? Yeah, it's a decreasing function, so wouldn't it be at its greatest when t is at its least? So at 1, this F double is 2. That's our m value. Do you see where I'm coming from? Okay, so the error bound is 3 times 3 times 3 times 2 over 12 times 3 times 3. Altogether, my error bound, not my error, my error bound, my error is no more than 1/2. That's true, the error was 700, so the error is not more than that. All right. Say I wanted to estimate the log of 10, natural log of 10, with error less than 100. How many trapezoids would I need to use? Well, let's start here. I know my error is less than or equal to b minus a cubed over 12n squared times m. If I could get my error bound to be less than 100, then wouldn't the error also have to be less than 100? Yeah? Okay, so I need to figure out how do I get my n big enough so that the error bound falls below 100 and therefore the error is less than 100. So I'm going to work around here. What is b minus a in this case? 9, yeah? Or 10 minus 1. Oh, you know what I really should do is first say, this is what the heck I'm doing. Log of 10 is the integral from 1 to 10 of 1 over t dt. Yeah, you should always make that your starting point. Sorry, what is n? Do we know it? No, that's the question. How many trapezoids is the question. What about m? Still 2. Will it always be 2? In what case would it not be 2? If you were estimating something less than 1. If you're estimating something less than 1, like a half, for example, then you would not be using 2. But in this case, it is 2. Alrighty, so n squared is greater than, we've got 27 times 2, so that's 54 with 2 zeros, right, over 12. So is that 900 over 2, 4,500, 450? Anyway, you just figure it out. What do you get? Oh, not 27, dummy. Oh, that's why I made a mistake. 729 times 2. Oh, this is not something mental. Give me your decimal. It's not 5,400. Sorry, that's stupid. I was thinking 3 cubed, not 9 cubed. N is greater than? This is not pretty. Imagine it's something in the hundreds ballpark, 3 decimals, or 3 orders. 111. What are the 3 decimals before rounding? 227. Okay. All right. If I need more than 110.227, and I'm supposed to answer with the number of trapezoids, then I say 110 or 111. 111. 111 or more trapezoids. Yeah? All right. Just to get a little Simpson's rule practice then. Let's say I wanted to estimate log of 5. I would use Simpson's rule because it's way more powerful than trapezoids. I'll get a far better estimate with Simpson's. So let's go. Let's first identify what I'm trying to do. In other words, communicate the calculus you're doing. Log of 5 by this new idea today can be estimated by using an integral from 1 to 5. All right. Now that's actually equal. Those are equal, but I'm now going to estimate the Simpson's rule estimate. The starting part of this is delta x over 3. So what's delta x here? The total delta is 4, but I'm dividing, that's delta x of each subdivision. So delta x is 1. Okay, delta x is 5 minus 1 over 4. So delta x is 1. The 3 is part of the weighted average idea. You're weighting midpoints 2 and trapezoids 1, which you don't need to remember anymore, but it's good to know. So how does it start? If I let f equal 1 over t, then the first is f at 1. The next is 4f at 2, then 2f at 3, and 4f at 4 plus f at 5. Okay, I remind you, you have to do an equal number of subdivisions for that pattern to hold. All right, so what is f at 1? 1. What's 4 times f at 2? It will be 2. What is 2 f at 3? 2/3. What's 4 f at 4s? 1. And what is f at 5? 1/5. What is my common denominators? 15. Okay, so 1/3 of. So 1 you had to multiply by 15. 2 you had to multiply by 15 to get 30. 2/3 you had to multiply top and bottom by 5, so you get 10 there. 1 you had to multiply top and bottom by 15. And 5 you had to multiply top and bottom by 3. What is your total numerator? Do I agree? 45, 55, 73. I agree. 73 over 15. So our estimate is 73 over 45. Let's see how we did. Excuse me. 73 divided by 45 is approximately 1.622. Log of, I forgot what problem did we do? Log of 5? Actual log of 5 is 1.609. So we're about 13 thousandths off. Pretty stinking good. That's pretty good estimate. We didn't even have to do that much work. We could have done a lot more subdivisions and that's even better. All right. That then is the ideas of the day. Good deal. How did 97 extra practice go? Are these volumes going well? Hey. Okay. Here are, I know the answers, so the key was up here yesterday, but here are the answers again if you did not see them. Let me know if you'd like to talk about 1 or 2, 3, B and C? 3A and B. I cannot hear it all. 3A and B. Cool. Any other 3A and B? Let me throw that over here. Okay, isosceles triangles are the hardest ones, I think. So you've got your log graph, you've got your cube graph and the region enclosed. So in 3a it says isosceles right triangles with the hypotenuse in the plane of the base parallel to the x-axis. So parallel to the x-axis goes like this. Hypotenuse in the plane of the base means they have to have two equal sides and a right angle for it to be isosceles right. And if the hypotenuse is in the plane, then the right angle has to be sticking up like that, yeah? All right. I get the idea, I think. Okay, so the volume is the sum of many area of the base times the heights. Question is, which do we use here? Base height divided by 2 or 1/2 AB sine C? I don't honestly know. It's not always the same for these, but what is the height, dx or dy? It's got to be dy because that's the thickness there. So dy either way. So I guess I could see this way because I know a side and the angle's got to be 45 here. But then the other side I don't know. Yeah, let's go here. Okay, so if this is the case, then isn't the base just the hypotenuse that's in the plane? Yeah. The hard part is the geometry of the height. Now, here's the deal. If this is isosceles, then these have to be equal 45-degree angles. And if I then split that with the height, that has to make a new smaller 45, 45, 90. And so what is the height here? Isn't the height exactly the same as half the base? So if the height is half the base, then base height divided by 2 is base half base divided by 2, or 1/4 base squared. I think that's the way to go. So here we go. 1/4 base squared is y. Now the last part is the what's the base? Here's the base segment, and it's right minus left, yeah? So is the right x cubed minus 4 or the log? It's the x cubed minus 4, but it has to be in y terms. So what is the right curve in y term? Y plus 4, yeah, cube rooted, yeah? So cube root of y plus 4 for the right minus e to the y for the left. And then I don't honestly, the intersection points are something like negative 3.999 and 0.501. Those are y values, obviously. Very cool.
Can you just use the same formula for the next one?
Unfortunately, though, the cross sections are parallel to the y-axis in the next, so no, you can. They are vastly different. So if the cross sections in the next one are parallel to the y-axis, then they go this way. And as far as the geometry, it's also different. Now it says the leg is in the plane of the base, so here's the right angle, and it's totally different. So this one, I definitely want to use base height divided by 2 here. Or should I do 1/2 AB since whatever? Any which way you look at it, isn't it just base times base divided by 2? Because it's isosceles and the legs are known. And the thing is, this dx or dy now? That's dx. So the integral will be 1/2 of the square of, and we just have to do what's upper minus lower now.
Yeah.
Seems like log minus cube, yeah? All right. And different limits of integration too. So, any other questions on this function? Good. So the test is Friday. I can't for the life of me figure out Mr. Ray. He says he's got a test Friday, but I've told them a lot of bio people say you don't have a test on Friday. So I don't know. Tell the guy to update his calendar for Pete's sake. I'm gonna go with the test on Friday, and it'll be through last week's stuff, so through this. Okay. Alrighty.
Oh.
Jack. You gonna leave this, try to leave this up? Hi. Yeah, probably best to keep it.
I'm doing something for stats Thursday, is Redler.
At 7?
Yeah.
What is that lesson? Maybe that wouldn't be a bad. It's up to you. You can take it after that. Or you can just make this test prep if you don't even want to sweat it because you got nothing. You can. Just let me know tomorrow if you need me to have the test ahead of time on Thursday in class. Yeah. Then just let me know. All right. Thank you. Hello.
I'm gone Thursday.
Okay.
And so I have no idea about like and all that, but I just couldn't get it.
Oh, okay.
So these are the problems I was doing yesterday.
Okay. Sure.
Yeah.
Okay. Yes, we can go. Yeah. Sounds good. Hi.
I was absent Friday.
Absent Friday. Have a nice day, people.
Mr. Mendel,
Yes.
9, do you have a little plus problem, but it doesn't specify how many steps? Just any of them?
No, that's where you're gonna have to do that first. Oh, I didn't say it, you have to. Just write it down. So, yeah, you start 16. Jackson, say 1. Alrighty. Have a lovely day.